Oh, good afternoon. Today we will be discussing inflection points. The inflection point is where the concavity is going to change. So let's look at example number 1. Now, in order to determine where the concavity is going to change, we're generally going to be looking at when the second derivative is equal to 0. So let's go ahead and take the second derivative of this function and then set it equal to 0 and solve for the independent variable. So here we go. Now this is just a polynomial function. So when we take the first derivative, we just take our exponents and move them to the front and then reduce them by the number 1, well, 1 unit. So we should get 12x squared minus 24x. Now keep in mind, that's only the first derivative. We need to take it one more time to determine what the second derivative is. So let's take it one more time. And so in this case, we're going to get 24x minus 24. Now, we've gotten all the way down to the second derivative, and I don't know if you recall the little chart that we have, but if the second derivative is positive, then that means the function is going to concave up, and if it's negative, that means the function is going to concave down. So a number can only have 3 type of signs. Either the value is going to be 0, or it's going to be positive, or it's going to be negative. So once you find out when a function is 0, everywhere else it has to be positive or negative. So let's first find out whether the function is 0. So let's set this equal to 0. And so remember, we have to set it equal to 0 and then solve for the independent variable. So this is a minus 24. So we're going to add 24 to both sides. So we get 24x is equal to 24. And now we need to divide by the number, or the coefficient, and so that's going to be divided by 24 on both sides. So x is equal to 1. So we know that our x value is going to be equal to 1. So this is where the second derivative is equal to 0. So now we're going to test that point to determine where it's positive or negative. So we want to see if the second derivative is going to be positive or negative to the left of 1 and to the right of 1. Now you can choose any number that's to the left of 1. I think 0 is the easiest number to choose. And remember, we're trying to see where the second derivative is positive or negative, because inflection points is going to be, again, where your concavity is changing. And when we're talking about concavity, generally we're looking to see when the second derivative is positive or negative, or when the first derivative is either increasing or decreasing. So I'm going to choose 0, and I'm going to plug 0 back into the second derivative function. So if I plug 0 into the second derivative function, everywhere I see an x, I'm going to get a negative value, because we have 24 times 0 minus 24. Well, that's just a negative 24. So we're going to get a negative number. Now, I'm going to choose a number to the right of 1, and so I'm going to just use 2. So if I plug 2 back in, then I'm going to get 2 times 24, which is 48, minus 24. That's going to be 24. That's a positive 24, which is a positive number. So you can see that at positive 1, the concavity changed from concaving down to concaving up. So let's just write this up. I know that f of x concaves down on negative infinity to positive 1. And this is because why? Well, you can see that the second derivative is going to be negative. So this is because f double prime is less than 0. But if you look to the right of 1, f of x concaves up. Why does it concave up? It's because your second derivative, and it's actually concaving up from 1 to infinity. So it concaves up on the interval 1 to infinity because f double prime is actually greater than 0. So remember, a point of inflection is just where your derivative, your second derivative, is changing either from positive to negative or negative to positive, because the point of inflection is where your concavity is changing. So let's just kind of get a picture of what that would look like on an actual graph. So if you take this graph right here, if you look at, let's just say this point is when x is equal to 5. Now if you look here, this graph is going to be doing what? It's going to be concaving down. Now another reason you can determine that this is concaving down is because your slopes are decreasing. These slopes here are positive, but eventually the positive numbers are getting smaller and smaller till the slope is eventually going to be 0. Now if you look here, these numbers become negative, but the negative numbers, the slope of these lines actually start decreasing as well, because up here you have, let's just assume this is going to be -1 up here. This slope is -1, but down here this slope is a little bit more steeper, so it's probably, you can assume that it's around -10. So these slopes are doing what? Decreasing. So that means f prime of x is decreasing. So this is going to be concaving down from here to here. And then if you look, so let's just, from 0 to 5, we see we're concaving down. But let's just go ahead and look at this value. From 5 to 10, you're going to be concaving up. So that means 5 will be a point of inflection, because the concavity changed from what? Concaving down to concaving up. So 5 will be a point of inflection. So let's just try to do one more example where we have a graph, and then we'll move on. So this time I'm actually going to give you the second derivative function, and then we're going to try to determine if the graph is concaving, what the points of inflections are. So let's look at this. Let's just say, assume that I gave you the second derivative already is equal to x minus 3 times x plus 3. So this is the second derivative already given to you, so you don't have to do any more work to get the second derivative. Now all we need to do is just set it equal to 0, determine whether the second derivative is positive or negative, and see if we have any points of inflection. So the points of inflection, let's find out when we have zeros. So when we have zeros, now since this is minus 3, I am going to take the opposite of the -3, so I'm going to get positive 3, and then since this is positive 2, I'm going to take the opposite of that and get -2. Alright, so now I just need to test points to the left and the right of 2 and to the left and the right of 3. So to the point that's to the left of 2, I'm just going to use -3. So if I plug -3 into here, I'm going to get a negative number, because that would be -6. And if I plug -3 into here, I'm going to get a negative number, because that is -1. So a negative times a negative is a positive. So this is actually going to be a positive number. Now choosing a number between -2 and 0, -2 and 3, the easiest number to choose is 0. If I plug 0 in, I get a negative number and a positive number. So a negative times a positive is going to be what? Negative. And so lastly, let's choose 4. Well, if I plug 4 into here, because 4 is to the right of 3, if I plug in 4, I'm going to get a positive number and a positive number. So a positive times a positive is going to be positive. So you can see that -2 and 3 are points of inflection because what? The concavity is changing. I just had a student about to walk out, so I just want you guys to know what I'm dealing with. All right, so let's continue. So let's just go ahead and write this up. I'm going to only write up one of the points of inflection because it's not really necessary to do both once you see the example. And so f of x has a point of inflection. Sorry, I spelled inflection wrong, but that's supposed to be a C. Now when we're talking about a point, you need to say the x and y value. So it's going to be at the point -2, comma, f of -2. And we don't know what the function is, so that's why I'm just saying f of -2. And we have a point of inflection because what? F double prime changes from positive to negative. Alright, so thank you guys for taking the time out to learn about points of inflection, and we will see you next time.